Aaron Micallef, Acque, dolci, offshore e il loro ruolo nella geologia marina. Prego.
Grazie mille. Adesso I'm going to switch to English because it's easier for me to speak in English. Sure. So good afternoon, and in the next 15 minutes or so, I'll try to provide an insight into the role of offshore fresh and groundwater in marine geology. But before I start with the presentation, I'd like to define what I mean by offshore fresh and groundwater, at least in my project and in this presentation itself. And to me, this is water with a salinity that is below that of seawater, and which is stored in pores of sediments and fractures of rocks in the subsea floor. Now, the first discovery of offshore groundwater actually goes back to the 1960s, when it was encountered during a drilling expedition offshore Florida. But it was only studied in more detail about 20 years later, when the US carried out a petroleum assessment of its northeastern continental margin. They drilled 19 boreholes looking for oil. They found little of that, but they found lots of offshore groundwater. Most of the boreholes up to 100 kilometers away from the coast. So since then, offshore groundwater has been documented in most continental margins, as highlighted in the seminal paper by Vincent Post et al. In 2013, which has actually triggered, or rather reignited the interest in offshore groundwater in the last decade. And I think there is a number of good reasons why we should focus our attention to offshore groundwater. From a scientific point of view, it plays a crucial role in global biogeochemical fluxes. It could be used as a potential proxy of environmental change, and it plays a role in the distribution of benthic and especially subsea floor ecology. From a more applied point of view, understanding offshore groundwater has implications for resource exploration, for geohazards, and especially geomorphology. And most interestingly of all, it is a potential and conventional source of fresh water in coastal regions. Now, in this presentation, I'm going to focus only on the geomorphology. And I'm going to do that by addressing three objectives. I'd like to first give you an idea of the characteristics and controls of offshore groundwater globally. Then I'd like to list the links that have been made in the past between offshore groundwater and submarine geomorphology. And I will conclude with the Markham project, the project I'm leading that is focusing especially on these topics. And of course, I'll start with the first one. And to address this, I put together a database of global records of offshore groundwater. There's a bit more than 300 of these, mostly derived from boreholes and core data, but also from some geophysical data. And what I did, I estimated like some dimensions of the groundwater systems and carried out very simple statistical analysis. And if you're interested in these, you can download the data from the link that I'm showing on the screen. But perhaps more interestingly, this is how the database looks like on a map. So you can see there is records of offshore groundwater almost everywhere, apart from Northwest Africa and the Indian subcontinent. And this is more likely because of the absence of, or rather the poor petroleum exploration in these areas rather than the absence of offshore groundwater. Now the map is shown as records by emplacement mechanisms. And I'd like to describe these in a little bit more detail because there are 5 of these. 3 of which are relevant to meteoric offshore groundwater. And these are active present-day recharge via a permeable connection, and where there is no discharge at the seafloor because of, for example, a confining layer such as clay. Then there is meteoric recharge during sea level low stands because of higher hydraulic heads, steeper hydraulic gradients, and more importantly, extensive shelves which have been exposed to infiltration from precipitation. And thirdly, it's the step of glacier to proglacial injection, which involves freshwater emplacement by melting at the base of an ice sheet, for example, or the formation of proglacial lakes. And of these is the second one, which has been most commonly been reported in the literature. Now, apart from these 3, there's an additional 2, which are responsible for non-meteoric groundwater emplacement, and these are Diogenesis, so transformation of minerals such as silica, gypsum, or clay, and the composition of gas hydrates, which is known to release low salinity pore water. Now, the database that I showed you earlier allows us to extract some global spatial characteristics of these systems. So the majority, not all of them, of course, occur within 55 kilometers of the coast, down to 100 meters water depth, and their top and the top of the groundwater is between 0 and 200 meters below the seafloor. They normally make up a number of bodies that are no more than 1 kilometer thick. And in terms of distribution, they are mostly located in passive margins and in silicic-clastic aquifers. And finally, the mean salinity of these bodies is 15 PSU. Now, when we have a good look at these systems globally, there is a number of common geological factors that seems to be controlling their distribution. And I'm going to list the 6 most basic ones. So we need most of the time a permeability contrast, so an aquitard overlying an aquifer to ensure that the offshore groundwater doesn't seep out the seafloor. There's connectivity at various scales, which ensures that there is extension of the freshwater to saltwater interface further offshore. And there's buried channels, which are high permeability conduits that actually can explain offshore groundwater in the outer parts of the shelves. Dissolution, especially in carbonate settings, which create preferential pathways for groundwater exchange. And then we have faults, which can act as both as conduits and as barriers, depending on the flow of the direction of the flow. And finally, we have overpressures, either because of onshore linkages or more likely because of sediment loading offshore. So those are the geological factors that are controlling the distribution, and there's a few hydrological factors as well to take into consideration. The key one is topographically driven flow, which is enhanced mostly during the sea level low stands. But we also have salinization, which is basically the adaptation of the groundwater system to sea level rise during via haline convection. And finally, we have geothermal convection, which is thermal-induced buoyancy that is most strong in the outer shelf and the upper slope. And finally, the question that I get asked most is, okay, so how much fresh water is there actually in the seafloor? And there have been a number of attempts to estimate this in the past. I'm trying to do it with the database that I mentioned earlier. So what I did, I used only the records with a meteoric recharge because it's simpler to carry out these estimations with that. And I took into consideration the offshore distance from the coast, the thickness of the body, and the porosity information that we have. And I calculated the mean volume of groundwater per kilometer of coastline for both active and passive margins, and I multiplied by the distance of total length, of these margins. And to cut a long story short, the volume that we get is 1 million kilometer cubed, which is slightly higher than previous estimates, but basically on the same order of magnitude. And this is to give you an idea, about 2 orders of magnitude the water that humans have used in the last 2 centuries globally. So it's quite a big amount. Okay, so that's what we know about offshore groundwater. Now, the second point is that I'd like to present is how this has been associated to seafloor geomorphology. And what I'm going to show you is a map of studies that have been carried out in the past where this has been done in relation to canyons, landslides, and pockmarks, which are the yellow, orange, and red symbols. The blue and the green is where we have meteoric groundwater recorded in boreholes or cores, as I showed you earlier. So there's a few of these studies, and I would like to summarize what they say in the next slide. So basically, the role of the groundwater is important both when it is in the subsea floor and when it comes out. So when it's still in the subsea floor, it can generate excess pore pressures, which are known to potentially reduce the effective stress and the shear strength of sediment, resulting in slope failure. And this has been documented mostly in silicic-clastic margins like Nice slope in France, or I'm showing you an example from the Norwegian fjords. It has also been suggested for volcanic flank collapses, such as in Hawaii. But here, the connection is a bit controversial, or perhaps it's only applicable in very special circumstances. Now, excess pore pressure can result in less extreme events. So if we have, for example, pore pressure fluctuations, this can result in the formation of the sediments in the form of fluidization or liquefaction or potentially creep. Now, when the water does seep out of the seafloor, we have, of course, different processes. We have the formation of pockmarks or semicircular depressions. And here what we have is the groundwater, when it's seeping out, it's exerting a seepage force on the sediments, offsetting the frictional force and causing the sediments to be eroded by the flow. And this has been documented in numerous sites around the world, especially in the North Sea and the Baltic. Where this process is recurring, and especially it's taking place on a slope, it has been associated to a retrogressive slope failure that might account for the formation of submarine canyons, as has happened in the Valencia margin, for example, as I'm showing you on the screen. So those are mostly the last two four-statistic cases. If we're looking at carbonate settings, the processes are similar, the morphologies are slightly different, because, for example, I'm showing you the case of the Campeche escarpment offshore Mexico, and here, groundwater seepage, this solution, both of them have been associated to the formation of box canyons, which are these theater-headed valleys with vertical walls and very wide exits, or potentially even some karstic features at great depths, exceeding 2 kilometers in the New Jersey margin, for example. So those are the associations that have been made between groundwater and landforms or submarine processes. There's a few gaps in knowledge, however, which make these connections a bit difficult to establish because, first of all, we have a poor understanding of the offshore groundwater characteristics, their extent, the distribution, the flow characteristics, and the dynamics of the whole system itself. And secondly, we have a lack of understanding of the mechanics that are required to create these particular landforms or to give rise to these processes, but also the rates at which they occur and the scales at which we can find them. And this is where the Markan project comes in, because one of the objectives of this project is to evaluate the conditions in which offshore groundwater can potentially be a significant geomorphic agent in passive continental margins. So to address these objectives, we're using a two-pronged approach. The first one is to understand the offshore groundwater dynamics, because this is still a big gap in our understanding. And I'm going to show you an example of what we did offshore New Zealand to address this issue. So I'm going to take you to the Canterbury Bight, offshore the eastern coast of the South Island. And we went there because in 2010, there was an IOTP expedition that showed a poor water salinity anomaly at 50 meters water depth. So we went there in 2017 with the Tangaroa. We spent a month exploring this shelf. And I'm going to show you a few of the geophysical data that we acquired. And this is going to be line 4 and line 7, which are perpendicular to each other. Line 4 is on the left-hand side, line 7 on the right. So from the seismic reflection data point of view, there's nothing super exciting here, really. I mean, this is what you would expect from a eustatically controlled passive margin. We have alternating coarse and fine sediments. What is more interesting, however, is the controlled source electromagnetic data, because we see these large high resistivity anomalies at depth and some smaller resistivity anomalies in the shallower section. And by actually integrating these two data sets and also additional lines which I didn't show you here, we can map the offshore groundwater system in 3D. And we can see that it extends 60 kilometers away from the coast, has a thickness of at least 150 meters, and a potential volume of about 200 kilometers cubed. We can also get some understanding.
3 minutes to go. 3 minutes to go.
Thank you. We can also extract some information on the origin of the groundwater system, because there's some geochemical data from the IOTP borehole. And I'm going to show you just one plot where we have bicarbonate and chloride, and the blue dots, which are taken from the offshore groundwater system, have higher bicarbonate and lower chloride than the purple dots, which are the seawater. So that's indicating to us that there is a meteoric component in there. But we also know that the age of the groundwater system along the coast is quite young. It's less than 50 years in terms of age. So it's very likely that it's actively recharging at present. However, the active recharge is not enough to explain all the groundwater system that I showed you. And I'm going to demonstrate this by modeling. This is a variable density model result from line 4, the one perpendicular to the coast. The gray arrow is where the coast is. And if we have the sea level at present for 1 million years, you get an extension of the fresh water offshore by 5 to 10 kilometers away from the coast, which is very small. But if we take into consideration the sea level fluctuations over the last 1 million years, we obtain dimensions that are more similar to what we observe in geophysics, about 60 to 70 kilometers from the coast, and the geometry that is more representative. And finally, we also have modeling of the age, where we can see that most of the groundwater has been in place in the last three glacial cycles. So the conclusion is that you need sea level low stands to enhance topographically driven flow to drive the freshwater offshore. So that's it from the offshore groundwater dynamics part. the geomorphology is a bit still shaky because we're still working on that. So I'm just going to tell you what we're doing. We're developing forward stratigraphic models for silicic, clastic, and carbonate margins. We integrate those with the groundwater models that I just showed you. Then we also implement geotechnical models to understand the slope stability and how all of this changes during glacial and interglacial cycles. And I don't have any results so far, but the preliminary results are indicating that during sea level low stands, you do get increased slope instability because of the groundwater. So to conclude, I just wanted to share 3 take-home messages with you today. And these are that offshore groundwater is a global phenomenon. It is directly regulated by sea level fluctuations during glacial and interglacial cycles. And ultimately, preliminary results are showing us that extensive groundwater bodies, especially during sea level low stands, can likely trigger slope instability in passive continental margins. And before I finish, I'd like to thank the European Research Council for funding my research in the past 4 years. Thank you for your attention.
Thank you, Aaron. Thank you very much for the beautiful presentation. Very, very interesting.